so we're not doing a quiz tomorrow. It's just going to be regular, like, learn more math stuff. We're sort of in the real meat of the course now. I imagine this is entirely new for most people, and this is the really important stuff, so we're going to spend some time on it. So with that said, we are beginning with 16.4, which is a chapter called Green's Theorem. All right, so Green's Theorem is maybe the most important theorem in this last third of the course material. It is a computational tool. It's a very powerful theoretical tool. It's going to be dissatisfying the way I'm teaching it today because the way the book does it and the way that my notes are set up is I'm going to tell you what Green's Theorem is today, and then we're going to do some examples and calculations with it. And there's some things we have to be careful of in the setup of the problems. And it's going to basically be a black box in the sense that I'm going to tell you the theorem is true, but not any idea of why. So I'll hint at why, at sort of what's going on. And you'll be able to see, I can give you hints, but I can't properly show you what I think of as the real version of Green's Theorem until I talk about divergence and curl of vector fields, which will be in 16.5, so tomorrow. So I'm going to tell you the theorem today, we're going to do a bunch of examples with it, and then tomorrow I promise I will tell you why it's true. Because I could prove this is a mathematical artifact, but the mathematical proof doesn't really shed light on how this was discovered. So Green himself was interested in electromagnetism. So this is work that ultimately led to some of the observations that built up to Maxwell's equations for electromagnetism. So interestingly, Green, I think, is almost entirely self-taught and turned out to be a profoundly important mathematician and physicist. So he's got an interesting biography if you go look him up. Okay, so Green's theorem is a theorem about the relationship between integrals on two different pieces of a domain. So what I mean by that is, if I write down some sort of figure like this, a region in R2, there's an inside of the region, D, and an outside of the region. And the outside of the region is usually called the curve C. C is called the boundary of D. C is the boundary of D. And the other mathematical symbol that we'll sometimes use if I want to really emphasize that I'm on the boundary of a region, I can use yet another abuse of the partial derivative symbol. If I write the partial derivative symbol next to D, I mean the boundary of D. That's what this means. That's the boundary symbol. Okay, so what we're going to be concerned about is regions in R2 that have simple closed curves as their boundary. So we're going to let D be a two-dimensional region with a boundary C that is a simple closed curve. All right, for such a region, I'm going to have to pick a direction to travel. And so the convention that mathematicians have decided on is that I am traveling around a simple closed curve in the positive direction if I'm moving counterclockwise. So this direction is the positive orientation. Positive orientation for a simple closed curve is counterclockwise. This is why mathematicians are bad at playing board games, because we think the natural order of turns should be counterclockwise instead of clockwise. Notice that this also corresponds with the way that we think about polar angles, right? Polar angles are determined counterclockwise from the positive x-axis. So this is on this. It's chosen to agree with that. Okay, it's possible that we can have regions that are more complicated than regions with simple closed curves, which means I need to lift the idea of positive orientation just slightly. So if you imagine that you had a region D that had a hole in it, now the boundary of the region is not a simple closed curve anymore. It's two simple closed curves. So this is the region D. The convention that we make now, if I call this C1 for the outside curve and C2 for the boundary of the whole, then the boundary C is equal to C1, that's the union symbol, which means both of them put together. The boundary is both of the curves. And if I want to traverse those curves in a positive direction, well, this curve on the outside, if I had traveled this curve in the counterclockwise direction, then the interior of the set would be to my left as I traveled. As I travel around this curve, the interior of the set is to my left, right? So in a more complicated region with a more complicated boundary, I'm going to set up the positive orientation to be the direction you would travel on a curve that keeps the inside of the curve to your left. So on this curve, we go this direction, because as I travel on the curve, if I looked to my left, that's where the interior of the region I was studying would be. On the curve on the inside, I have to go the other direction, because if I went that way on the inside and I looked to my left, I would see the interior of the region that I was studying. One of the more amusingly difficult theorems to prove in higher level mathematics is if I drew a curve like this that was closed, it has an inside and an outside. That's the Jordan curve lemma. A simple closed curve has an inside. You have to do like graduate level mathematics to prove that. Because it's easy to say, but then you think about what does that even mean? What is the inside of something? Okay, so what Green's theorem is going to do is it's going to relate two different kinds of integrals. If I had a region that looked like this, I can define two different types of natural integrals on the setup here. I could think about the double integral over the region D of some function f dA. That sort of integral would work in the interior, right? A double integral of some scalar function is a really natural thing to do on the interior of region. I have another type of integral that I could set up here on the boundary, which would look like the integral over C, maybe of some vector field ds. So there's one type of integral that's easy to define on the inside, a dA integral, and a different kind that's easy to set up on the outside. If I'm traveling around a curve, I have a different kind of integral. What Green's theorem is going to do is show us a relationship between two specific integrals here. An integral of a vector field around the outside of the curve and a specific integral in the interior. So let me state it. So we're going to let f be equal to a vector field p of xy, q of xy. P and q are the sort of traditional letters for this. And if I wrote down the integral around C in the positive direction, that's what the plus means there, so positively oriented curve C, of the integral f dot dr, one way I could write the integral of f dot dr would be the differential notation for this, which is the integral over C plus of p dx plus q dy. Those are the same thing, right? If f is equal to pq, then f dot dr is just p dx plus q dy. These guys are called circulation integrals. Because what they're measuring is the work done if I go around some curve in the positive direction, and I have some vector field attached to the curve, and I calculate that integral, what I'm calculating is the work done as I traverse the curve and come back to where I started. As I travel along the curve, it's the amount of work done moving through the vector field. Now, if that was a conservative vector field, the answer would be 0. If you were working in gravity, it wouldn't matter where you ended and where you started, right? You would just be where you started and there would be no work done. But lots of vector fields aren't conservative. So an interesting one would be, because of the way that, say, air works, when things cut through it, the circulation integral around a wing is not zero. Wings produce lift because that loop is not zero. Right? So this is one, there's a lot of vector fields that are not conservative. Fluids compress. Things rotate. So circulation integrals show up in the study of vector fields all the time. And the insight that Green had was, motivated by wanting to study these things, motivated by wanting to study circulation integrals, he noticed the following theorem. So, if we, so this is actually one statement of Green's theorem. I think this is sort of the less intuitive version of the theorem, but I'm going to state it the way it was originally done. If D is a simple region in R2, so that is a region with a simple closed curve for a boundary, and C plus is its positively oriented boundary, positively oriented boundary, and F is equal to a vector field PQ, is a vector field. Probably it needs to be of class C2, which means 2 times continuously differentiable. Then the circulation of F around the boundary. Oh, hold on. I'm giving you the wrong version. I gotta give you the textbook version. The integral around C of P dx plus Q dy, which is the circulation of F around the boundary, is equal to the double integral on the interior of the scalar function dq dx minus dp dy dA. This statement right here is Green's theorem. Okay, first question I got for you is, does that look familiar? Have we seen that before? dq dx minus dp dy? That showed up yesterday, I think, or on Tuesday. What do we use it to measure?
If the vector field is conservative.
So this is a quantity that picks up if a vector field is conservative, right? So if this was 0, if the vector field was conservative, that would tell you the circulation integral would also be 0. Traveling through a vector field on a closed curve in a conservative vector field gets you nothing. So what this quantity is measuring is the failure of a vector field to be conservative. So if the vector field is not conservative, that won't be 0, and there will be work done as I go on a closed loop. Okay? So I think Green's theorem is sort of hard to get your mind around. If you want a hint about what this theorem is actually saying, and we'll revisit this maybe at the end of the class, a little preview is this is going to turn out to pick up the curl of a vector field, or the tendency of it to rotate at points. So if a vector field has local twisting, that's how you get circulation. So the big picture version of Green's theorem, the way that I think about the theorem is, Green's theorem says the tendency of a vector field to rotate on the inside of a region is equal to its circulation on the outside of the region. So it's sort of an inside-outside theorem. But that's what I'm going to talk about in 16.5. Once I've told you about curl, I'll be able to give you the physical intuition that makes this true. Okay, for now, what we should do is some examples of the application of Green's theorem. So what you should think of in the original run of Green's theorem, your initial exposure to it, is it as a calculational tool that is used to compute otherwise very difficult integrals. This was invented originally, you could think, as I give you a difficult circulation integral, and instead you throw it away and you replace it with an easier double integral. All right, so here is an example. Oh, now why did I not hand out notes to you guys today? It's because there is no paper in the department office. So these are all posted online, but there's no paper, so I can't print anything. Saving trees. So let's let C be the rectangle let's see, x goes from 1 to 2, and y goes from 2 to 3. I guess this is a 3 here. That won't turn out to matter in this case. Let's compute the integral over c oriented in the positive direction of the vector field 3x to the 4th plus 5 dx plus y to the 5th plus 3y squared plus 1 dy. So if I gave this to you in chapter 16.2, you should be furious at me. Because if I want to calculate a line integral over a rectangle, I have to parameterize every side of the rectangle. If we're doing this with our earlier technique, you would say, okay, so I go from this point to this one, to this one, to that one. I got to travel around the outside of the rectangle. It changes definition 4 times. So just on this first part, C1 right here, I have all points of the form t comma 2, where t goes from 1 to 3, and so I would have to do, okay, so r of t would be equal to t comma 2, and so r prime of t is 1, 0, and then I have to take this integral and I have to put, okay, well, these are the x's and these are the y's, and so just for the first piece, I'm going to have to write down the integral on C1, just this first part of the curve, where I write, 3 t to the 4th plus 5 times 1 dt plus this thing with a bunch of 2's plugged in all over the place. There's a 2 to the 5th and a 3 times 4 and a 1 times 0 dy. And then, dt. Is it dt? And then, but I've parameterized it so it goes from 1 to 3. Then I do that 3 more times. Yuck. We should be more elegant than that. So what is the elegant solution to this? The elegant solution says, if I could use Green's theorem here, am I on a region with a simple closed curve as its boundary? I am. I'm sitting over the top of this rectangle. Yep.
Could you do the thing that we did on Tuesday, where we just go from start to finish and then start to finish?
That works in this case because this turns out to be a conservative vector field, but it's only because it's a conservative vector field that it works, right? So path independence, which is what you're asking about, only holds because this one turns out to be conservative.
If you could prove it.
Yeah, if you could prove it was conservative, then you know the answer would be 0, right? Because it wouldn't matter the path. If I start and end at the same point, the fundamental theorem of line integrals would say that you had 0 as the answer. But let's say you didn't know going in that it was conservative. It should be the first thing you check, right? So, but yeah, I mean, it's that the precise reason why this integral is going to be easy to compute is exactly what you're saying. So if I did Green's theorem here, Green's theorem says that if this was P and this was Q, that I can replace that integral on the outside rectangle with the double integral of the inside of dq dx minus dp dy dA. So I can switch out a parametric integral, and people hate doing these because they're nitpicky, for a double integral over a rectangle of a scalar function. That's as easy as these things get in the double integral setting. So what is dq dx? Well, if q is equal to y to the 5th plus 3y squared plus 1, there's no x's in there. dq dx is 0. On the other hand, if p is equal to 3x to the 4th plus 5, dp dy is 0. I've made a really dumb problem, but boy, oh boy, are these nice to put on exams. So easy to grade. dq dx minus dp dy is equal to 0. And that means that horrendous 4-component thing that I was trying to compute can be replaced with an integral that's the double integral over the rectangle. So we're integrating from 1 to 3 and 2 to 3 of 0 dx dy. which is 0. And you can imagine, you don't want to be the person that spends 30 minutes doing this parametrically and getting 0 as the answer, and looking at your friend and they've written that down. So, let me reiterate what we did right there. We started with the integral over c of p dx plus q dy. We observed that it's a closed curve, so I can apply Green's theorem to it in the positive direction. And that says that I could replace this with a double integral over the inside of the rectangle of dq dx minus dp dy. But since that quantity was 0, we get 0. It doesn't always work this easily. Like, it's nice when it turns out to be 0, but it's not always true. All right, so let's get another example here. So one of your hints that you're looking at Green's theorem is if I give you something where it looks insane if you parameterized it, that's a pretty good hint that you're supposed to be using a technique that is not parameterize and plug in. So here's another one. Let's evaluate example 2. Let's evaluate the integral around c positively oriented of f dot dr where c is the circle x squared plus y squared is equal to 1. And the vector field f is equal to minus 7x squared y, comma, 4x plus e to the y squared sine y. Now, I don't know about you, but the thought of parameterizing the circle with sines and cosines and then putting them out into that function makes me shudder. I don't want to calculate e to the sine squared times sine y. I don't see an obvious u substitution that's going to make that work. That's going to be impossible. Yeah, sine y. It's even worse. The sine of the sine. So, you could, presumably, if you wanted to, you could write down r of t is equal to cosine of t sine t, and then just imagine plugging that in for the y values. E to the sine squared times the sine of y. Or you could say to yourself, is the domain that we're or the curve that we're integrating over, is it the boundary of a nice region? I'm integrating over this curve C. Is that a simple closed curve that is the boundary of a nice region? Sure looks like it to me. It looks like it bounds the unit circle. So there's D right there. So Green's theorem says that the integral around C with positive orientation of f dot dr, which is equal to the integral around C of p dx plus q dy, by Green's theorem, I'll write GT here for Green's theorem. Green's theorem says that's the double integral on the interior of dq dx minus dp dy. And if your math professor is a nice guy, on an exam question, you're really hoping that that dq dx minus dp dy turns out to be really nice. So if I read off p and q from the vector field, dp dy is equal to minus 7x squared, I think. No, yeah? What, am I mixing problems? Hold on. Oh my god, I'm mixing problems. Hold on. This was supposed to be easy. There's two problems on my notes that are right next to each other, so I picked the curve from one of them and the function from the other one. So, all right, to save myself, there's a rhetorical move that I wanted to make here. So, I'm going to replace this with what it was supposed to be. 2y plus e to the x, that's much nicer, and x plus the sine of y squared. Remember, you can't integrate the sine of y squared. Okay, so instead of dp dy being some nonsense, what is dp dy now? This is not a negative, this is a 2. It's 2. And what's dq dx? 1. So what's dq dx minus dp dy? 1 minus 2, negative 1. Oh, so Green's theorem says, since I've gone out of my way now to fix the problem into something that might show up on a test, Green's theorem says that I could write this as the double integral over that circle of minus 1 dA, which means I could pull the negative 1 out if I wanted to. And now I'm looking at the integral over a region dA. So it's a double integral over a region with nothing in it. What does this represent? It's the area of D, right? The double integral of D, dA, is the area of D. So this is minus 1 times the area of D. Now, if you want to, you could put this in polar coordinates and integrate it up as a double integral, or you could observe that the region we're integrating over is a circle of radius 1. So what's the area of the region D? Pi. So this whole thing is minus pi. You solved an integral without doing any integration. The best kind of exam questions. Okay. So that leads me to another point here, which is this integral, for this particular vector field that we chose, we got out an expression that just represented the area of the region that we started with. Maybe we could use Green's theorem just to write expressions for area. So this is sort of example 3 or talking point 3 here. Can I find a vector field F so that dq dx minus dp dy is equal to 1? Because if I could find one of those things, then it would be the case that the double integral of dq dx minus dp dy would be equal to the double integral over d of dA, which would be the area of D. So if I could find a vector field that had the property that dq dx minus dp dy was 1, I could use Green's theorem to just calculate the area. What's a really easy vector field? And if I want to calculate area of a region, I want that vector field to be the easiest possible vector field in the world. Can you think of one?
y2x.
Oh, easier than that even.
Oh.
Remember, the derivative of a constant is 0, I think.
Oh. y0.
All right, that'll do it. F is equal to y0. Does that get you?
Yeah. No.
Does that make you negative 1?
Oh wait, yeah.
And really, we want to put a 1 here because we want this to be a vector field thing, right? So I don't want to have a direction that disappears. So if I stick in a y1 here, I need a non-zero vector field, right? So if I put in y1 here and I make that negative, or I picked the field 1, x, both of those fields have the property that dq dx minus dp dy is 1. And what that would say is the following things are true. These are sort of novelties. The area of D, which is equal to the double integral of dq dx minus dp dy, oh, if that's a 1 dA. What Green's theorem would say is that if I chose this vector field, I would have the integral of dx plus x dy over the boundary curve. And that's pretty easy to compute. And this one would be minus y dx plus dy. So these are sort of cute formulas for the area of a region in terms of the length of its boundary curve. Man, that's a weird idea. This says I can tell you the area of a region by calculating something to do with the length of its boundary. So I didn't have a chance to prepare this in something I could project. The fact that these area formulas are true, this one in particular, where I'm just adding x times dy. There's a tool from the 1950s called a planimeter. And what a planimeter does, I encourage you to look these up because these things are awesome. If I had a physical one, I actually went looking on eBay to see if I could buy one, but they all cost like $200. The idea is, if I gave you a region D with a boundary curve C, you can build a device. It's got like a pin that holds it to the table, or a clamp, and then it's got an arm that pivots, so there's a rotating arm right here. And then there's a stretchy arm attached up here, like an arm that can slide in and out, so this arm moves in this direction. And attached to the end of it is a pen. And what this thing does is, if you take that pen and you trace a physically written curve on a piece of paper, it calculates this. It knows your position because it knows where it is relative to where you started. It can keep track of your dx, dy. It's got little clicky wheels that pick up units of dx and dy. As you move the pen, one wheel that spins this way picks up how far you move the pen up and down, and the wheel that spins this way figures out how this happened. And when you're done drawing the curve and you get back to where you started, the number on the dial that adds these numbers up is the area of the thing in the interior. It's freaking amazing. Like, it's sort of like that somebody invented this. Like, so yeah, it's just the dumbest version of Green's theorem gave rise to a really elegant physically engineered mathematical tool. So I encourage you to go look at these. They're beautiful devices, and like the translation of like mathematical ideas like this into physical machines is always a fascinating one for me. These are up there. These are better than slide rules. I have like a 8-foot tall slide rule in my garage too, but I'll bring that in sometime. How many of you guys even know what a slide rule is? Oh man, okay. We'll talk about, maybe I will bring in my slide rule. It's a mechanical multiplier, an exponentiator. So it's a ruler that has a slidey bit inside of it that would let you very quickly multiply like things of large powers, like natural logs, exponentials, and whatnot. Yeah, they're cool. Anyway, okay. So this is sometimes part of some professors' things that they want you to know. I want you to like be able to be comfortable with the idea that choosing the correct vector field will give us an expression that gives rise to area. There might be homework on this, but I won't ask you an area question on an exam. You don't have to memorize this formula or anything. It's just kind of a cool application. All right. So the last bit with Green's theorem that I want to show you, the last example, is probably the most sophisticated example, but also the most widely used. And that is, sometimes I can use Green's theorem to find contour integrals on curves that aren't closed. So that's example 4. Here's that gnarly thing I wrote before. Let's let f be equal to the vector field minus 7x squared y, 4x plus e to the y squared cosine of y. And I really like to know the integral of f dot dr on the curve C, where C is equal to the arc of the parabola minus 2 phi, or from y is equal to 9 minus x squared from minus 2 5 to 2 5. So the curve I'm integrating over this time looks like this. So this is the point minus 2 5, and this is the point 2 5. I have some vector field that I've attached to this land, and I want to know the work done as a particle travels that curve dictated by y is equal to 9 minus x squared, subject to that vector field, that force field. But it's not closed. So I can't use Green's theorem. If only there was a way I could close it. So it's not closed, so we make it closed. So I could close it, though, by putting in, I'm going to make this a different color. I could put in this line segment. So I could close this region up with the curve y is equal to 5. And the idea would be, there's no Green's theorem yet. All I'm saying right now is if this region was closed, this is the curve C1 that I started with. Here's my new curve C2 that I've added. The positive orientation here runs this direction and this direction. The theory of calculus that I'm using here is going to be the integral of the whole thing is equal to integral of the pieces added up. So the claim is if C is equal to C1 union C2, that is if the boundary curve is both of these things done in a row, first do C1, then do C2, then the double integral over C of, not the double integral, sorry, the integral over C of f dot dr is equal to the integral over the first part of f dot dr plus the integral on the second part. Integrals pull apart into pieces. This is how parametric integrals work, right? The integral on the first part plus the integral on the second part equals the whole integral. So this one is the one that sucks. You can imagine parametrizing this thing and then plugging that up into this function is going to give you an impossible integral. The y's up here, I mean, e to the y squared cosine of y, that's not a function we have access to. So that integral, if I just did it by itself, this is the original problem, and it sucks. It's going to turn out to be the case that the integral on C2 is pretty easy because the y variables don't change. Notice, all of the complications of this problem come from the y variable, but on this line segment, y doesn't move. And Green's theorem tells us, now that we've made it into a closed region, now I can use Green's theorems to say this is also equal to the double integral over d of dq dx minus dp dy dA. And this integral is going to turn out to be easy to solve. So we have an integral that's terrible plus an integral that I can solve is equal to another integral that I can solve. So basically, I can figure out what this integral is equal to without integrating it. I write down an equation with two pieces I can do, and that will let me isolate the part that I can't compute directly. Okay, so what we're going to do is we're going to start working on the other two parts of the problem and hope that they work nicely. So we're using this closing trick to apply Green's theorem. First thing we'll do is the integral on the green piece there. So the integral on C2 of f dot dr. I do have to do a parametric integral here because it's an integral on a line segment. On that line segment, r of t is just equal to, let's see, the y's are constantly 5, the x's are moving, and the t values go between 2 and -2. R prime of t is equal to 1 comma 0. Oh, that's nice. And so if I plug this x and this y in to my vector field f to calculate this integral, I get the integral from -2 to 2. Okay, so f with t and 5 plugged in is going to be minus 35t squared. And the other variable, I'm going to get a 4t. And then I'm going to plug y equals 5 into that, which is just a number. Just a number. So when I plug in y equals 5, I get e to the 25 times the cosine of 5. And then I'm going to dot that with the vector 1, 0 dt. R prime of t dt. This is the calculation of a line integral. And notice what that means is there's a 0 in that component, which means this is even though that's a constant, I don't even care. It's not there. 0 times something is 0. So this integral turns out to be the integral from -2 to 2 of minus 35t squared dt. And that's easy. I think it turns out to be something like minus 35 times 16 over 3. Just an integral polynomial. Okay, so we got this guy right here, which means now I know what this is. I know that this is minus 35 times 16 over 3. Hopefully, I can also compute that guy. Well, let's see. The double integral over d of dq dx minus dp dy, and of course I erased the vector field, sorry, where f was minus 7x squared y, was it 4x, 2x? What's in the second slot?
4.
It's 4x, okay. 4x plus e to the y squared cosine of y. If this is p and this is q, then dq dx is 4. And dp dy is 7x squared. That's a polynomial. Can we think of, the next question is, okay, I've reduced this to an easy integral of a polynomial over some sort of region D. This is the region D that we're integrating over now. That looks like kind of one of those simple regions where it's bounded by functions. So I could write this as the integral from minus 2 to 2 of the integral from 5 to 9 minus x squared of 4 plus 7x squared dA. That's an easy integral, right? One of these sort of double integrals over a general region type setups. So I'm going from minus 2 to 2 in the x direction, and from 5 to 9 minus x squared in the y direction. So this is like dy dx. And that integral is not hard. That's annoying because there's algebra to do, but it's not hard. So in the interest of time and sparing you like me foiling polynomials out, I'm going to say that this is easy enough to compute that I'm going to call it n, for where n is whatever quantity you get out when you compute that thing. And that means now I know this part also. Whatever number that is, I can compute it. I'm integrating a polynomial. So what this results in is an equation. I have the original integral that I could not solve, the integral over c1 of f dot dr, plus an integral that I could solve and did, minus 35 times 16 over 3, is equal to an integral that I also could solve. And that means that the integral that I don't know must be equal to n plus 35 times 16 over 3. It's a trick. And in practice, the way these tricks sort of work is you might think like, well, that's like you just set up a problem where you knew that it was going to work out this way. And of course, that's how it works in a textbook. What working engineers, applied mathematicians, and researchers will do, and this is not something generally a computer does in a lot of scenarios, is the selection of the way that we finished the curve is what made this work correctly. I chose that horizontal line segment because I saw it would make that part easy. It would destroy this part of the term. And I also looked at it and said, well, Green's theorem might be accessible here because if I take the derivative of this with respect to x, all that goes away. So this is like almost like an art thing as opposed to an algorithm. Green's theorem tells you the method. Selecting the particular equation to solve is something that you learn from practice. But the idea of taking something that is not closed and then making it closed to solve the equation is the key idea here. Yep.
Is there any case where you want to go like the other way?
From the region to the curves? Absolutely. Yeah. Yeah, every example I gave you in here is in the direction. Here's a parametric integral and it sucks. Replace it with an area integral. But there are, in fact, that area formula that I wrote down is one of those ways, right? I would like to know the area of this region. I've got the integral of the function 1 dA. If only I had a vector field that would let me do it parametrically, right? That's exactly the other direction. So yeah, it's a two-way street. Right, so the last thing I'll say, and this is not going to be rigorous at all, the preview of what we're going to do next time is I recognize I have given you no idea why you should believe this theorem is true. I just said it. I have declared Green's theorem. Right? So it turns out physically the reason it's true is because same thing I said before. Physically, if I have some region in space and I could measure all of its local tendency to rotate, and I could somehow add up all of its interior rotation, that corresponds to circulation on the outside. That is physically what Green's theorem is telling you. That if I could measure all the little rotations of the interior of a region, then the way that it acts on the outside is the sum of the way that it's acting in the interior. Another version of the theorem says if I have a bunch of flux through a curve, right, a vector field passing through a curve, if I could tell you all the little fluxes in the interior and I added them all up, it would tell me how much of the vector field is penetrating the boundary. Both of those are ways to interpret physically what Green's theorem is saying. So that's what we'll do next time. I'll talk about curl and divergence, and I will show you what I think are the physically meaningful versions of this. And if you're a math student and you want to see the real proof of it, I can point you to the right direction on that too. All right.